One way to indicate the wind data is through the windrows. Windrows is basically it's a graphical representation of the wind data. In this particular example, we're looking at the wind data from Bakersfield in California in the month of July. We use the month of July is because it's the hottest month. Most of the air conditioners are running. So if you want to design something, we want to design it for the worst possible case. And these are the data which have been accumulated over 60, 70 years. And it just in one diagram, it tells you where the direction of the wind is. In this case, from the northwest, most of the wind is coming. And what is the average wind speed? These are different colors, and then the frequency of those are the circular diameter that they show the frequency of the wind at different time. So by looking at this thing here, I can say that most of the wind is coming from the northwesterly direction at the range of between 5 to 10 meter per second. And then I can say, for example, between 16% and 24%, circa which are 8%, so 8% of the time, the wind is in the 8.5 to 11 meter per second, which is the blue color. So it's a very convenient presentation that gives you speed, direction, and frequency all at once. Wind turbines, they operate on two basic principles, the drag type or the lift type. The drag type is like a cup anemometer. Basically, it blocks the wind and the wind is pushing a blade. If you stick your hands out of the car, you can feel the force of the wind, and the wind wants to push your hand away, and that is the same way that the drag wind turbine work. The Persian windmill is a drag type windmill. Lift type wind turbines are the type that you use the difference between the pressure between the two sides to produce a lift. And this is what causes that wind turbine to move. Once you have the wind, then of course the wind turbine captures the wind and is turned. The wind turbine is connected to a generator which produces electricity. The wind turbines are usually contained of a tower on top of which a housing is being installed called nacelle. Inside the nacelle, there are gearboxes, the generator, cooling, unit, anemometer, and all of the control equipments are there, and is connected to a rotor in front of it. That's how the wind turbines are packaged. The diagram at the right shows, that as the wind passing the blades, because of the curvature of the blade in one side is different from the other side, is more curved on the top than the bottom. The pressure at the bottom is higher than the pressure at the top. That would cause the lift, and this lift in this case is in the plane of the paper and toward perpendicular to the blade surface. That's where the direction of the rotation is, and that's how the wind turbine is operating. In the horizontal axis wind turbine, the blades are usually designed to maximize the lift. In vertical axis turbines mostly work on the drag. The advantage of the vertical axis wind turbine is that they can capture the wind in any direction, so you don't need any kind of mechanism to turn the wind turbine to a particular direction to catch more wind. As I mentioned, most of the wind turbines are drag type, but there are some that they can use in the recent last few decades that they use lift, And the disadvantage of vertical axis wind turbines are that they cannot be operating on their own. They're not self-starting. And so it has to be started maybe by a motor up to getting to a certain speed, and then they can start. Efficiencies are usually smaller. They can operate on a lower elevation, so you do not need very big tower, and but they produce a lot of torque. These are some of the examples of the vertical axis wind turbine. The one in the left is the cup anemometer. Usually we use this kind of anemometer to measure the wind velocity rather than extracting power from it. The one next to it is called Savanius. These are the two blades that they are forming a S-type shape. The wind is cut through it and we're rotating. Darius is more lift type anemometer, very, very light. They can move much faster. These are also called the egg beater, as the shape suggests. Gyromill and Windspire are different variations of this kind of wind turbine. This is a horizontal axis wind turbine. The diagram at the right is the largest wind turbine that we have. It's installed in Germany. It's the world's largest. The diameter is about 126 meters or 413 feet and produces 7 megawatt of power. Over the period of a year, on the average produces 60 million kilowatt hour, and that's enough for every 5,000 German home for one of these wind turbines. In theory, we can only have one blade, but 2 blades and 3 blades are more common. It's because they will be helping in making the basically balance easier, and so that's the one that's usually used. More blades, usually they do not work very well because one blade falls in the wake of the previous blade and they will interfere and they reduce the efficiency. The turbine has to be installed away from the major obstacles like the houses and trees, and this is a diagram which has been suggested by the Department of Energy, that they gives you the wind turbine have to be in a area that there's not wind, there's not any obstacles, and so they have to be at higher elevation and farther away from any building. The higher elevation is actually better because the higher elevation, the wind picks up, so the efficiency will be higher. The disadvantage is, of course, you need a much bigger tower, and towers are very heavy and expensive. There is a certain amount of power which is in the wind. The faster the wind is, then of course it has more kinetic energy. The more wind is going through the blades, then there's more mass and the total kinetic energy also increases. The denser the air is, then of course more mass goes through here. And so overall, when we put everything together, we will find out that the wind basically contained in any wind stream increases the power, increases with the air density, with the area of the blades, which is like the square of the blade diameter, and changes with the cube of the wind velocity. So the speed is the biggest, most important factor. After that, the diameter goes, and then is the air density. Of course, we don't have much control over the air density, but from this analysis, we can say the same wind turbine produces more, maybe 10 to 15% more power in the winter than it does in the summer, because the air is heavier in the winter. So this is one example that what is the effect of different parameters is. Let's say you have wind turbine, diameter is 3 meters and generates 10 kilowatt of power when the wind speed is 4 meters per second. Now, if the wind speed goes to 12 meters per second, that means the speed is 3 times. Then the power would be like a cube of the wind speed, like would be 27 times. So if we reduce 10 kilowatt at 4 meters per second, the same wind turbine produces 270 kilowatt at 12 meters per second. Same way, if we double the turbine diameter from 3 meters to 6 meters, then the area would be 4 times bigger and the power would be 4 times as much. So if it produces 10 kilowatt at 3 meters, it will produce 40 kilowatt at 6 meter diameter.